everyone see now? Yep.
Okay, thank you
Amazing.
so much. Sorry
Sounds
about
good.
that, everyone.
No, wait. So I'm going to be, again, talking about a few of the lessons we learned. And long story short, it was quite difficult. And our implementation is still not complete. And I'm going to be talking about a few of the obstacles remaining and what were the hardest bits and what were some of the surprises that we got. Right. So in the early days of May, DeepMind released and published Nature, AlphaFold3 in Nature, as most of you already know. And there was a big controversy on why the Nature allowed it to publish it without the source code. Now, when I first saw this, it had felt like they didn't have to publish it, and a lot of the supplementary information seemed so comprehensive that I was just grateful that they published what this whole network was about. But as we started implementing it, I saw a few of the reasons why source code has to be published along with code because along with the paper because sometimes mistakes happen, and the only way of correcting those is checking it against the actual ground truth. So a brief timeline: in the 8th of May, AlphaFold 3 published in Nature. There was a big gap as people started working on it, and the first implementation came from Baidu, and they released Helix Fold under a non-commercial license. We were also working on it, and that kind of propelled us to say, okay, maybe we should not wait for the entire project completion, but we had found some interesting things. Let's just release those. So we released as Ligo Biosciences an incomplete, but we fully open sourced everything. So there was no commercial restrictions. You can still go use the code for your research. All of the model components are implemented. You can go use them. There are no restrictions whatsoever. Then Joshua from and the Chai discovery team released Chai 1. And they did an interesting thing where they released a web server. So you can still use Chai 1 through a web server, and you can use it for commercial purposes as well, the web server. But you can't see the model code, and the model running sort of scripts in GitHub only allow you to do things for non-commercial purposes. So uh, that's also, I believe, a way of getting pharma companies and these partnerships with commercial companies uh, for access to this model. Then more recently, Protein X released the source code, which was quite exciting. It's a non-commercial license, but we can actually see what exactly the model is doing, and it's in PyTorch, so it's much more readable than, let's say, Baidu's implementation in Paddle. And more excitingly, the source code finally was released, obviously under a non-commercial license, and the weights are being distributed on a sort of case-by-case basis by DeepMind. So that's a brief timeline of this whole thing. Now, there are a few features of AlphaFold3 that make it hard. So DeepMind went the bitter lesson of deep learning. They from AlphaFold to completely simplify the architecture and went for scaling. So they scaled compute, data, and the model. That makes it expensive. For reference, the whole model was trained on 256 A100 GPUs, and the rough estimate of training is, without counting the data preparation costs, which is quite significant, about 200 to $500,000. So it's quite expensive. It looks like, and from the AlphaFold source code now, it's looking like an insane amount of effort went into the data pipeline. So in the paper, they actually do 4 fine-tuning stages, and they can merge and manipulate biological data with very mature, sophisticated pipelines. And I'm sure that Isomorphic Labs is using this to power their sort of next generation models, and yeah, they're using it as part of their research infrastructure. This is one of the hardest parts to implement, and dealing with the wealth of structural data in the protein data bank and the AlphaFold database. It's very difficult, and also compute intensive. So for example, training on the AlphaFold database requires that you have the multiple sequence alignments for every protein that was already predicted. Now, DeepMind had this around because they were the ones who built this database anyway, like in the first place. But recomputing this, if you actually try to do it on CPUs and like if you just take the CPU costs of just do some back of the envelope calculations, it actually comes out to be in the millions. So like millions of dollars just to compute the multiple sequence alignments for the training data. This is before you train the model. So that's also quite like expensive and a big limitation. And another thing is the model itself is transformer based. So a lot of the architectures use attention and very attention-like components, but it's not quite a transformer. So none of the luxuries of flash attention and sort of linear memory consumption or other optimized kernels they can't be used out of the box with AlphaFold3. So that makes things very, very difficult because you can't just write the PyTorch definition of a model and expect it to scale to 256 GPUs. It will be very inefficient. It will cost a lot. And this is, by the way, a tweet from Tim Green. Sure, AlphaFold3 is cool, but have you seen the structure class? Like emphasizing that the data part may have been the actual hard part in this implementation. So a brief look at the model. The pair form is essentially AlphaFold2, except for a few simplifications. So instead of for those of you who are familiar with the architecture of AlphaFold2, this single attention with pair bias was a bit more complicated. It used to process the entire multiple sequence alignment row-wise. They got rid of that, simplified everything, but the triangular updates and the triangular self-attentions are exactly the same. So this is like a very streamlined architecture, and it's very simple to implement because we already have the building blocks from OpenFold and AlphaFold to source code to get this right. And the training is quite stable because we know like the gradients will flow well, there won't be bugs in the implementation. So this is quite simple. Now, the only problem with it is it scales cubically with the number of residues, but that's another problem. The diffusion module is the new bit in AlphaFold3, and it's at least 10 times harder than the pair former to implement. It replaces the structure module and it gets rid of the frame. So in AlphaFold2, every residue was represented by a frame and a rotation. Famously, in AlphaFold3, they completely dump that and they use atoms directly. And the reason they can do that is because they use a generative training paradigm. If you just use atoms with no frames and no like additional auxiliary losses that ensure that the chain is correct, then because of the averaging out behavior of a regression loss, things get blurry. So there might be clashes, there might be things that you wouldn't find in natural structures, but if you do a generative training paradigm, then all of the local details are very sharply defined. So this allows them to completely dump the frames and switch to an all atom representation. Now, there are some interesting things here. They build on the diffusion transformer. And this was a paper that showed that scaling transformers on generative tasks also beats more specialized architectures like UNIS, which were the predominant architecture at the time. And they also use things like sparse local attention to constrain computational requirements. And that's in the atom transformer. Now, an interesting thing here is there's an error in the pseudocode in the architecture definition, which results in unstable training. And it's includes a missing residual connection. So on the left here, what you see is the actual diffusion transformer block from the paper of Peebles and Z. And this was the paper that first introduced the DIT block. And here it takes in the input tokens, performs multi-attention and has a residual connection here. And this residual and then it does a sort of point-wise feed-forward NLP stuff. But the first residual connection is missing. So in the diffusion, if you look at the pseudocode, the first residual connection actually doesn't exist. It looks like the entire attention is coming directly from the input tokens, and there's no residual connection. Now, when I first saw this, I didn't realize that, like, I suspected it might be a mistake, but it also was learning. It wasn't compromising training that badly. Experimenting with both, if you actually have the residual connections, training is a lot more stable. So you don't get many loss spikes, and also the gradient flows are a lot better. So like introducing the residual layers gives a better gradient flow and convergence. And this was one of the things that we pointed out in the initial Twitter announcement. Now, in the AlphaFold3 source code that was released very recently, the residual is there. So this is actually a typo, and it was the paper that was wrong, not the architect. This wasn't an architectural decision. In the AlphaFold3 diffusion training, the authors used the framework of Karas et al. From 2022. It has very favorable properties. So you can actually have a variable weight skip connection that allows you, as you get closer and closer to very low noise levels, where the structure is like more or less right, there's just a little bit of noise left. The network can just predict the noise and do very fine refinements. But if you're at much higher noise levels, then it's very hard to like predict the noise that will cancel the noise that's sort of dominating the structure. So instead, you can just predict what you think is the final output. So they have interesting variable weight skip connections, and there are a few things that allow neural networks in general to train more stably. You have unit variance of network inputs, and the training target is also unit variance. The authors introduced a loss scaling that gives you unit loss at initialization for all noise levels. Now, interestingly, in AlphaFold3, by the way, how this works is you get the ground truth, you just noise it out, run the diffusion module. There's some complications with you have to permute. If you have multiple chains you have of the same copies, you have to permute them in the correct way. Or if you have like you do the permutation and then you apply a very simple mean squared error loss. But then you have to weigh that loss properly. So that loss weighting is this one. So the authors say we apply first the diffusion loss, which is the loss mean squared error. Then this is supposed to be like this weighing function is supposed to make everything unit loss at initialization, like make all of the loss values be the same at different noise levels, so everything's very stable. But here there's an addition instead of what we expect to be a multiplication. This is a typo. And if you don't fix this, then nothing trains. So without that loss correction, if you don't spot that this is a typo and correct that, then you can't train the network. And the reason is like here you can see in red the sort of loss weighting in the paper, and the new weights are in blue. So, and this is the noise level. So as noise level increases, it becomes very difficult to predict what the actual denoise output is. So you can actually downweight those samples. But as you get closer and closer to the ground truth, then it should be very easy for you to predict what the actual structure is. So then the loss weighting increases. But if you use the wrong scaling, then you're actually scaling the high noise levels at a very high weighting. So that completely messes things up. And the example, like how that manifests is, if you can see the bottom left of the screen, on the very left is the actual weighting in the paper. So there are huge spikes. And Yeah, I apologize for this scaling here, but that number is 800. So the loss spikes to like hundreds or sometimes thousands, and it's not stable at all. If you do the fixing, if you do the fix, then the loss starts at units, about like around 4, and then decreases very stably. So that's the difference that it makes. And this was one of the things that we pointed out in the initial thread, and more recently, Protein X included this correction in their technical report as well. Now, AlphaFold3 source code doesn't exactly include this because they don't have the training code, and this like the loss calculation is only included in the training code. But if you want to train AlphaFold3 like models, beware. This is not quite right. Now, model efficiency is quite important because the full training costs about $200,000. So even if you can shave off about 2 times, like if you can accelerate network training by 2x, which is quite simple to do because the naive implementation is so inefficient, it saves you 100K. So you get smart quite quickly about how you can make this network more efficient. Now, AlphaFold3 is transformer-like, but it's not quite a transformer. So it has things like when you're doing the query and key sort of dot product and computing the attention scores that you're going to average the value vectors with. When you're computing those scores, they add a bias from a pairwise representation tensor. So that makes it like impossible to use flash attention out of the box. So you have to write your own kernels. That gets really tricky. We got away with it by using the kernels of AlphaFold. So they had already developed flash attention like kernels that were incorporating the pair bias. So in the pair former, I got away with it, but in the diffusion transformer, you have this sparse attention pattern, and you have to attend to atoms in this sliding window manner, and that's very tricky. So that you can't use the sort of open folds or like deep speed for science kernels there. So that becomes a big thing that slows down the network. That's quite painful. And there are a few like JAX. So DeepMind writes their code in JAX. We're writing in PyTorch. So there are a few JAX and PyTorch platform differences. So when you're doing, for example, in the MSA module, they changed the MSA processing from AlphaFold2 to AlphaFold3. In the AlphaFold2, it's quite central to the entire network, and it uses attention here. It doesn't quite use attention. It's something, it uses something like attention, but there is no query and key dot product. So all of the values that you're going to use to average the value vectors come from a pairwise representation. Now, if you implement this naively, you allocate in the GPU memory this humongous tensor. So that tensor will have like the shape of the MSA representation, and it will be broadcasted by another like number of residues dimensions. So it becomes absolutely huge, and it scales really terribly with the number of residues and the number of MSA sequences you have. So that was a big bottleneck. And I first noticed this when I was doing some ablation experiments, swapping in deep speed for sciences like attention kernel and attention, which is supposed to be in the paper. They say attention is more expensive. And this was like a cheaper alternative to attention. When I swapped that in, the memory consumption went down 4x. But I didn't, how did that happen? And then when I investigated, it turns out this huge tensor was getting allocated. So that was one of the things we had to solve. And we solved that. This was a contribution of Alex Zhang. And in collaboration, we wrote a Triton kernel. So Triton is a language that allows you to program the GPUs. And the only thing this kernel is doing is just avoiding the intermediate tensor allocation and really, really just doing all of the calculations that you need to do and writing the final tensor into memory. So there's like you avoid all of this intermediate stuff getting written back to the GPU memory. And the results of that were quite incredible. So the PyTorch MSA pair averaging implementation, you can see in red. So with the number of residues, when you reach about 700 or so, your peak memory usage just from this module, this is like not including any of the other model components, reaches about the memory limit of an A100. So those of you who are running protein or running AlphaFold on A100s, you will know that an A100 is quite expensive. So you really want to, and using two A100s is quite tricky because you need to talk between like GPUs and stuff. So you really want to be able to get away with a single GPU doing all of your structures. If you have a module in your network that's consuming all of the GPU memory, I mean about 700 residues, then you can't predict anything above that. And this isn't, so in AlphaFold3, this isn't even residues, this is number of tokens. So if you have things like ligands or multiple complexes, you're very limited about by what you can do. So the Triton MSA implementation was much more memory efficient. So it allowed scaling to about like 4,000 before it reached the same memory usage. And there's probably a lot of more memory savings that can be done. But this was just like as an initial approximation, it was a good solution. And it saves this amount of memory and it's also faster. So it's like quite significantly faster in this runtime. So the baseline is the PyTorch here. So, I apologize for the coloring. The colors are reversed here. But the baseline is the blue one. The Triton kernel is here on the right, the red one. So it scales much better than the naive implementations. So there are very neat, like when you're doing AlphaFold3, it's not just about the math. It's not just about the algorithms. It's not you're not done when you implement everything in PyTorch. You actually have to think about how you put the thing on the metal in copper and wire, and how that's actually going to work in terms of its efficiency and things. So that was one of the challenging aspects that I didn't quite appreciate when I was first starting the project. Another problem, this is a general problem with deep learning, is that deep learning fails silently and often mysteriously. So this is an example. In green, you can see there was a bug in the data augmentation pipeline. But initially, I didn't know where this bug was. So all you see there is you have these mysterious looking spikes. The network seems to be generally training, but you have these mysterious looking spikes that eventually make your network diverge. And you don't know why it's diverging there. It's quite mysterious. Like, no idea why it goes more or less stably barring the spikes until there and then diverges. Once the bug is fixed, then no more spikes. Everything trains very stably and it doesn't diverge. So deep learning, if you don't write your tests properly, if you're not paranoid about all of the little silent bugs in your code, becomes tricky and becomes very frustrating after a while. And this is just an animation of the model after all of this. This is an animation of the diffusion trajectory as the model is sort of creating the proteins. So it's quite a small protein and very early in the training. This was after about 4,000 training steps, but it still had some protein structures emerge, which was quite satisfying. And when we reached this point, we thought we had enough to do a preliminary release, and we put out our findings to the Twitter community. All open source. If you're interested in using it in your research, you can use it. And I hope I'm not over time, but yeah, we can do questions if anyone's has any.
Awesome. Thank you so much, Arda. I think at this point, if anyone has a question that they would like to speak up, feel free to unmute yourself. If not, put it in the chat and one of us will read it out for you.
Hi, Arda. I have a question.
Hi. Yep.
So like to feed your diffusion transformer, what is the thing you're using? Like, is it like embeddings from your paired transformer, or is it more like some other information is